in R, which corrects that return to our view. And this method is called the Black-Litterman. Now the question is, who has on Excel or these things someday in your life in past did some Black-Littermans or similar things? Like tried, yes, looked at that. So what is that? It is quite statistical, but it has assumptions, which, where is that? Here. So I don't want, there are many researches and papers on that. It has its own, of course, cons and pros. It's better to know, cons and pros. Now the pro is that it combines the market realization of those assets with the views of, let's call them investors or portfolio managers. So you have a chance to incorporate your view. Views can be incorporated in different ways. For example, it's easier to do that on, let's say, sometimes on fixed income securities, a bit harder to do that on equities, but it gives you a chance to do that. Because the classical models, they don't give you a chance. They say, okay, what was realized in the past will be very good solution for the future, which is not usually true. That's what we are struggling at universities, yeah? Don't tell that this will be true, yes? Again, this is not ideal solution. It will not solve all the problem, but it gives us a chance to integrate our views. Now, how subjective are those views are up to us. We're not talking about them, we're talking about how can we do that in R. So basically, the pitfall of this model is that it relies on normality. And there is another model, which is based on copulus, and there is a package in R for that, which doesn't rely on any distribution. It just solves that through the joint distributions and so on. Okay? But overall, it gives satisfying results. Overall, it integrates okay. So let's say 70–80% is okay. You can fine-tune that and so on. You have to think, does it work? So what it does, the classical model does the reverse optimization and calculates the equilibrium portfolio. What does it mean? So, because you have weights currently in the market, which are in the market, yeah, and market usually should be always right. Is that true? We don't know, but current situation in the market reversed back through a reverse optimization to returns which fit that current allocation in the market. This is done through this. These are matrix multiplications, yes, scalar matrix. And then it combines that with the views. So how it is realized, and then we get the final distribution, posterior.
Views are like forecasts, expectations.
Yes. Yes. And you can ask me now, how can you forecast? But it is very, by the way, that is a very good question, and the answer is, for fixed income, it's much easier to do that for longer term. What do you think? Yeah, for longer term. Why? Because if you have, let's say, duration of 4 to 5 years, and you have yield for that, and if you are dealing with asset allocation portfolio for longer term, let us say, you can also consider all these roles and so on. But if you, let us say, do that for longer term and hold to maturity, you will get this.
And what about defaults, crises?
You take into consideration default rate, but you don't know what will be the exact default rate. But the more quality bonds you have, the more precise they are. The less quality, you usually put some cushion on that. Let us say it was, let's say, 2%. You put, let's say, 3% default rate cushion, for example. It depends on which segment you are doing. You can put 10%. Again, these are investment kind of considerations, how much default rate. But usually, this must consider default rate, hedging costs, swaps, all these costs and all these things, and you put them together, but it is another story. It is finite. We can discuss that together, but again, after maybe this arc, if you... Okay, so we get this final posterior kind of distribution for each asset. And that is the idea of Black-Litterman. Now, how it is realized in R? Quite straightforward. We have I use parts of this. It's Black-Litterman and Coppola opinion pooling methods. Yeah. Again, it's a package with functions. So basically, these functions, what they do, they calculate this weird formulas. So, for example, Black-Litterman formula is this. I don't want to sit and calculate it. I can, but we don't want to do that. And that is why it's easy to use the package which is already written. So, where was that? Black-Litterman. So it is, let's say I put here for our purposes risk-free rate 0. I do here the reverse. I did it by just different research. Basically, it's very good. One was, and here I just apply those functions. Risk aversion is calculated also. Here I put rule of thumb. In this case, I don't do precise numbers. Rule of thumb, it will be some 3 to 5 approximately. Yeah. What I do, and I also put here market caps from a rule of thumb, basically here. We can also omit it. It will not be a big problem. We have different other methods, but I show you the classical way. So what it does, it calculates prior excess variance covariance matrix and prior equilibrium means, and we get the prior equilibrium means. So for example, well, it's not. Yeah, it gives me this prior equilibrium means solutions. Yes. Then I need a function which basically calculates all those stuffs. What I do here, I write a wrapper. This is my own wrapper because the Black-Litterman will need. I now loaded my wrapper. It wraps another function which is posterior estimates. So basically posterior estimates is from this package, and I use this by wrapping it and transmitting my own arguments, right? What I need peak matrix, then I need view vector, and I will say what they are. Then, okay, prior moments and confidence vectors. What are they? So, view vector means that what views I have on that. For example, here I put US bonds will return 0.5%, for example. Europeans will be -1%, for example. Yes? Again, these are up to you. And so on. Yes? Emerging market equity will be 6%. These equities, European will be 5%, US will be 4%, and so on. After, let's say, hedging costs, all these things. Here, for demonstration purposes, how we integrate the views. Then, I have to show the confidence vector. Now, the cons, the weak part of Black-Litterman is it's not always intuitive. So these numbers are not intuitive, but the idea is here, how am I sure that this returns will realize? The simple idea is the confidence is taken as reciprocal, or 1 divided by its, let's say, variance. So the more variable is the asset, the less confident I will be. Which is kind of logical, but it is not intuitive. The other one solves that in a different way, but it is more complicated. I don't show it here. So I have the confidence. You see, it will be like these numbers, which don't tell us anything, right? These numbers. But in fact, the less this number, the less I'm confident in my view. Okay, so I have now posterior moments calculated, and I just can plot it. It took some time. Plot this. And it show me how things changed. Yeah. So these are historical returns suggested by classical Markowitz or classical optimization. And here we integrate our views. We say, okay, no, it's not true. This will be somewhere here. But again, these views are adjusted for also variance covariance metrics. This is not just the return figures we put. It takes also into consideration the market situation and historical correlation between the assets. It takes it into consideration, which is basically good, which is better than if we just, yes.
But can you also put in your views on the variance of a specific asset, or just how to say extrapolate it from the?
We can do that, but we can do our views on variance covariance metrics, the full, yes. But usually you can omit it. Usually, because the variance covariance structure usually over longer term will be much more stable than return figures themselves.
But if you have specific information that
Yes,
you
we
trust
can.
about an asset, that the mean will stay the same, but the variance will be much bigger,
Yes.
can you embed that?
Yeah, you can incorporate that. You can put it into. I guess you can combine it also between prior and then posterior. You can just change posterior.
Okay.
Yes. Because it will give you the posterior variance covariance, which you can just adjust up to your views, basically. Yeah. But I would suggest changing not posterior but prior, so that these are taken into consideration in calculating posterior returns expected. Okay. So then, okay, if we kind of have it, so these are return. This is the most difficult thing we struggle to find in practice usually, yes, and that is through Black-Litterman we can approximately find this structure, and we significantly downgraded it. You see, yes, it's not so historical things are significantly changed. In this case, we can influence it. So what we do, the last thing is just optimize it. Yeah, and let's just run it. It will run some minute or so. And after that, we'll just have, again, optimized portfolio. But again, in practice, it doesn't necessarily you take the optimal portfolio suggested by the model. You take the whole. You can take in practice, yes, the whole, let us say, for example, frontier, and build your portfolios on that frontier. Okay, so it calculates, and we have few steps to show visually. Maybe, meanwhile, questions.
Big question.
I need coffee.
The answer is probably positive.
What's the question?
What researches or tests were made to define predictive power of any of these approaches? For example, if we have views, are they at least somehow predict something, or are they just random and we can put any random numbers inside and maybe results will be better or the same?
Okay. Would you like to co-author me? Yes, no. I wanted to tell you after this all, but now I will tell you. First of all, I haven't seen kind of academic paper research on that, because every house, every investor will have their own views. And the question is, which kind of views are more stable. Based on, for example, yields, based on earning yields, or based on models which incorporate the valuation levels with some, you understand, cycles and so on. No, I haven't seen such, but now my next step is to wrap this and then probably the Coppola approach, because there is no backtest written in packages. So I want to wrap it into my own backtest function and backtest it through the time by using different expected kind of expectations, yields or different other things, and testing how they are performing. This is for me also the question which one will perform better.
Because predictive power is the main thing. If you have some some predictions, finding the optimal portfolio is like a technical question. But main thing is to find these numbers and I think this really like econometric problem.
Yes.
You can just take all you have and test it, and I doubt that the results will be significantly enough.
I can tell you one interesting thing, which I was also denying, but then I tried, for example, just without any views, historical, and they did better than naives, which is interesting. Then I checked, of course we were checking, I don't know, 10 years of these papers, which one performs better or not, naive or monkey portfolios or not. They are tricky. They write like this: okay, we can construct monkey portfolios, and of course some of them will perform better. But the question is, which monkey should we choose? This is the question. Of course, you can have 10,000 monkeys, and 10 of them will create excellent portfolios. But how you know in advance which monkeys are they?
It depends on the percentage of these monkeys who outperform the views. If you have 50% of monkeys correct, so
Yeah, but then you have again to backtest it, right?
yeah.
Yeah, you have to backtest those monkeys, but then they are monkeys. There is no monkey. They're just random. So what we need, consistent. Overall, the answer is mostly yield to maturity, and so based they will work.
High yield, yes, it's
Yeah, it will work.
right.
Equity is a bit harder, but again, there are models which incorporate, as I told you, the valuation levels, the mean reversion, some of this. Longer